These are the schematics for Roland's TR-909, an iconic drum machine from the mid-1980s. I've been staring at this absolute maze of components for a while now, trying to figure out how I can save this vintage 909 I bought last year. While it worked just fine initially, the kick quickly started to misbehave. To try and troubleshoot, I began breadboarding parts of the schematic, isolating different sections to understand what's wrong. But while doing that, I got a little carried away. Instead of fixing my machine, I ended up creating something new. An FM drum circuit that combines the punchy character of the 909 with the metallic textures of FM synthesis. Let's hear what it can do. To understand how it works, we'll retrace my steps and start by isolating the core concepts of the 909's design. First up, the oscillators. Compared to the TR-808, Roland decided to step up their game here. Because where the 808 used bridged T oscillators, highly efficient little circuits capable of producing percussive sine wave hits with just a handful of components, the 909 uses full-blown VCOs that generate continuous triangle waves. This shift was no accident, of course. Roland tried to compete with sample-based drum machines like the Lindrum, so they needed the 909 to sound much more realistic than the robotic and sterile 808. This forced them to bite the bullet and trade efficiency and lower manufacturing costs for a more complex but also more flexible subtractive synthesis approach, which starts with a proper VCO. And though the 909's kick, snare, and tom oscillators implemented in slightly different ways, they are all variations of the same basic idea. Combining an integrator, a Schmidt trigger inverter, and an injection point for a control voltage in a feedback loop to generate a triangle wave. Here's my slimmed-down take on this idea. This section is the integrator. This one's the Schmidt trigger inverter, and this is the injection point for our control voltage. It works like this. We'll assume that the Schmidt trigger inverter starts out latched into the low state, disabling the NPN transistor. At the integrator's non-inverting input, we get exactly half of the control voltage, and the op-amp will do everything it can to keep the inverting input at the same level. So as the control voltage pushes a current through the upper resistor and into the capacitor, the op-amp will pull the same amount of current out of the cap on the other side. This way, the voltage on the left will stay at half of the CV, while the voltage on the right will steadily drop. This keeps going until the integrator's output crosses the Schmidt trigger inverter's lower input threshold, causing it to latch into the high state. This enables the NPN transistor, allowing current to flow from the integrator's inverting input to ground. How much current? Well, we know that the voltage difference between the CV and the inverting input is the same as the one between the inverting input and ground. Simply because the op-amp will make sure the inverting input stays at half the CV. We also know that the resistance on this path is about double the resistance on the other. So the current flowing from the inverting input to ground must be double the current flowing into the input. And for this to work, the op-amp needs to provide the missing amount of current, which conveniently is exactly as much as is flowing in from the CV, causing the integrator's output to rise at the same rate it was previously dropping at, until it hits the Schmidt trigger inverter's upper input threshold and the whole cycle repeats. At the integrator's output, this creates a triangle oscillation whose frequency is determined by the CV.
because if the CV rises, both the current flowing into and out of the integrator's capacitor increases by the same margin. To test our VCO in practice, I've already set it up on Labor, which is a circuit prototyping tool I developed in collaboration with Synth. Check the linked video if you want to find out more about it. Also, if you want to follow along, both Labor and a DIY kit with all the necessary components are now available in the Synth webshop. Links are in the description. Alright, on the oscilloscope, we can see that the integrator does produce a continuous triangle wave. Using this potentiometer, which I've set up as a simple variable voltage divider between 12 volts and ground, I can adjust the control voltage. As expected, the oscillator's frequency changes along with the CV. Great.
Since triangle waves sound a little too buzzy and bright compared to an actual drum hit, Roland needed a way to remove the harmonics above the bass pitch. But instead of a low-pass filter, they decided to go for that simple Waveshaper,
which uses just a couple resistors and diodes to turn their triangle wave into a somewhat dirty sine wave. To understand how it works, let's assume that we apply our triangle to the resistor on the left. Then the other resistor going to ground will scale that triangle down, from around 10 volts peak to peak to just 1.6 volts peak to peak. Or rather, it would if it weren't for the diodes coming up from and going down to ground. Because as the triangle tries to push past the 400 millivolts line in either direction, the respective diode will gradually open up and sink or source more and more current. This will gently shave off the tips of the triangle, turning it into a rough sine wave, with the exact shape determined by the amount of scaling we apply. Too little and the tips become flat. Too much and they become too pointy. For our triangle wave, the amount of scaling is just right though. The Waveshaper gives us a pretty decent sine wave on the oscilloscope that's noticeably less buzzy.
There's only one problem with it. It's not percussive at all. This is one of the key advantages the TR-808's bridged T oscillators had. They produced sine waves with gradually decreasing amplitudes. To mimic this, we'll need to set up a proper VCA and use it to modulate our sine wave's amplitude.
Normally, VCAs are pretty complex. Even the simplest designs use plenty of components. But in typical Roland fashion, the 909 engineers found a way to boil things down to the bare essentials. Their VCA uses just 4 components: one op-amp, one NPN transistor, and 2 resistors. In essence, this design is just a regular inverting amplifier, but the input resistor has been replaced with an NPN transistor as a fake voltage-controlled resistor. For this to work, the input signal needs to be extremely low in volume, just around 20 millivolts peak to peak. Then the transistor will be locked into its saturation mode, where a large current flows into its base. This current's ultimate direction is then modulated by the tiny oscillation at the transistor's collector. When the collector voltage goes high, some base current flows out of the emitter, and when it goes low, it flows entirely out of the collector, while also dragging current from the emitter with it. This way, the transistor converts an oscillating voltage into an oscillating current of varying intensity, depending on the current we push into the base. In practical terms, if we increase the voltage applied to the base resistor, there is more base current to be modulated, and so the current swing at the emitter gets bigger. Now, because the op-amp wants to keep the voltage at its inverting input near zero, it will adjust its output voltage to neutralize the current swing. Essentially, it converts the swinging emitter current into a swinging voltage. And since the emitter current depends on the base current, we can control the output signal's gain by changing the base voltage. And that's it, we've got a VCA. Of course, since most input signals will be way too loud to keep the transistor in saturation, we'll also add a strong voltage divider at the VCA's input, which can conveniently double as the scaling resistance for our wave shaping circuit, since it's essentially just a 2K resistance to ground. To test this, I've connected Labor's variable voltage source to the base resistor. Right now, it's dialed down to 0. Let's see what happens as I turn it up. As expected, the output's gain increases with the control voltage. But there is one small issue. The output waveform has a positive DC offset that appears to be tied to the control voltage. What's up with that? Well, the issue is that when the collector voltage is 0, current is being pulled into the emitter. And the higher the control voltage, the more current flows backwards. This forces the op-amp to counteract, giving us an elevated output voltage when it should actually be neutral. How do we fix this? Easy. We neutralize the backwards current flow by connecting our control voltage to the emitter via a big resistance. Now, the issue here is that the exact amount of backwards current varies quite heavily between different transistors, even using the exact same model. So instead of trying to select the perfect resistor value here, we'll combine a 1 megaohm baseline resistor with a 2 megaohm precision trimmer. This way, we can dial in the ideal amount of compensation current for our specific transistor. Right now, our sine is still pretty off-center, so let's fiddle with the trimmer for a bit. And yeah, that looks pretty well centered to me.
Great, but our circuit still doesn't sound like a drum. To get there, we'll need to add an envelope generator to drive our VCA and turn the static sine wave into a quick percussive burst.
The 909's envelope generators are mostly just a diode, a capacitor, a potentiometer, and a small resistor. We can copy this straight up. If we now apply a trigger to the diode, the cap will fill up instantly and then slowly discharge via the potentiometer and resistor. This generates a falling voltage curve, whose steepness depends on the amount of resistance between the cap and ground. The small resistor ensures that we don't create a short circuit at the pot's minimum setting. If we now connect the envelope's output to our VCA's control voltage input, we should be able to shape the static sine wave into a percussive hit of varying length. To test this, I'm using Labor's manual gate, which has a dedicated setting for generating triggers.
Sounds like a decent starting point to me. But before we can refine it, we'll need to talk about triggers some more. And that's because, unlike Labor, most other gears sends out gates, not triggers.
So to make our circuit compatible, we'll want to add a gate-to-trigger converter. For this, we can adapt the circuit I used in all my previous percussion circuits, which is a little easier to understand than Roland's solution for the same problem. The linked video has an in-depth explanation, but here's the basic gist. The circuit uses a high pass with an added diode coming up from ground to turn an incoming gate into one quick positive spike. Then that spike is converted into a proper trigger, a quick pulse jumping from low to high and back using a comparator. Finally, that trigger is sent into an accenting circuit, which allows us to limit the height of the pulse to a given control voltage. If we now use the accented trigger to drive our envelope generator, we can use this CV input to set the volume for each drum hit. Here's how this sounds with a gate and CV sequence from my sequencer. While it does work, you probably noticed that the sound's transient, or attack, changes pretty dramatically between hits. We can also see this on the oscilloscope. The start of each hit looks different every time.
That's because our VCO is always oscillating and could be at any point in its wave cycle when the trigger hits. And the further it is from 0 volts at that moment, the louder the clicking sound.
Roland had the exact same issue, of course. They decided to fix it by resetting their oscillators whenever there's an incoming trigger. It works like this. First, we bridge the integrator's capacitor with an NPN transistor and a 10K resistor. Then we connect the NPN's base to the unaccented trigger via a 1 megaohm resistor. Now, as long as the trigger is low, the transistor will be disabled, and the oscillator will operate as it normally would. But if the trigger goes high, the capacitor discharges via the bridge, and the voltages on both sides will equalize. And when the trigger goes low again, the bridge will be disabled, and the oscillator will start its wave cycle from this point, which is exactly 1/2 of the CV, by the way, since that's the voltage we apply to the non-inverting input. This way, every trigger should produce the exact same output, because we always reset the VCO to the same starting point. This seems to work just fine. Both audibly and visually, all the individual hits seem to be much more consistent. Great.
That said, our drum still sounds pretty flat. It's definitely missing that characteristic 909 punch. To add it, Roland used a simple pitch envelope to modulate the VCO's frequency, which is much easier to implement and more reliable than it was in the 808's bridged T architecture. Another big reason why Roland decided to switch gears here.
Looking at the 909 schematics, the pitch envelope is basically identical to the other envelope we set up, except there's a resistance before the capacitor. Here's how it works. When we apply a trigger to the input, the capacitor gets charged with a very slight delay, making the rising edge less steep. Then the cap discharges just like it did in our previous envelope. By sending the output to the VCO's control voltage input, we force its pitch to quickly rise and then drop back down. This is a basic simulation of what a beater hitting a drum would sound like. And because an instant rise sounds too aggressive and artificial, we add the small resistor before the cap. Now, here comes the tricky part. We need to mix the pitch envelope's output with the existing control voltage we use to set the oscillator's base pitch. In the 909, Roland set up a full-blown summing mixer for this, which I'd like to avoid to keep our circuit small and lean. So instead, I'll go for a passive mixer using 2 resistors. The relation between those resistors will determine the intensity with which the envelope affects the mixed output. Because this is an important sound design parameter, I'll also add a big 1 megaohm series potentiometer to the pitch envelope path, which will allow us to dial its intensity down to almost 0. Also, I'll set up another diode after the envelope's output, so that it only affects the total mix if the envelope is higher than the tune CV. This way, we will always drop down to the set base pitch, and not lower. For the trigger, we'll use the unaccented one again, since the pitch bend is integral for the output to sound like a drum. Making it less noticeable on an unaccented hit doesn't sound quite right to me. Though maybe it does for you. Give it a shot. One final thing. For the pitch envelope to have an effect at all, its peak needs to be higher than the tune CV. Otherwise, the diode will block and the output will stay the same. Because of this, I'll add a 33K resistor above the tune CV potentiometer, limiting its maximum output voltage to around 9 volts. This saves us a little headroom for the envelope to do its job. That sounds way more 909-ish already. If I tune the VCO really low, we can get some decent kicks out of our circuit.
Still, it's missing the 909's sharp attack. Roland did multiple things to add it, and I've cherry-picked 2 of them.
We'll start with an enhancement to the triangle To Sine Waveshaper, which Roland kept exclusive to the toms. Its purpose is to distort the sine wave momentarily when the trigger hits, adding high-frequency content and extra volume for an aggressive impact. For this, we bridge the 10K resistor with a smaller resistor and another NPN transistor. Now, when a voltage is applied to the NPN's base via a big resistor, it allows forward current to bypass the 10K resistor. This selectively reduces the amount of scaling we apply to the input, which causes one diode to open up more quickly and widely, resulting in a much sharper cutoff at the positive tips of our triangle wave. Since we want this to happen for a little bit longer than the trigger duration, we'll set up a basic envelope. While experimenting with this, I found that there is a sweet spot for the ideal duration, so we'll omit a decay potentiometer and let the cap discharge purely via the transistor instead. For the trigger, I think it makes sense to use the accented version here. This way, unaccented hits stay a bit more mellow, while accented ones become more harsh. Because the effect is subtle, we'll do a direct comparison with and without impact distortion.
For me, the distortion adds some much-needed complexity to the sound's transient, making it much more characterful. Though I'd still like to add a little more spice to it.
The 909's kick injects white noise mixed with a trigger pulse into the output to achieve this. I'm not keen on adding a dedicated noise generator though, so let's try and see how far we get with injecting only the trigger. Doing this is really easy. We only need to connect our trigger to the Waveshaper's output via a diode and a relatively big resistor. For me, a 39K seems to be the sweet spot. The added attack is noticeable, but the trigger doesn't overpower the rest of the sound. The diode is necessary because the trigger drops down to -12 volts when it's inactive, which would noticeably tamper with the Waveshaper's operation. Also, I decided to use the unaccented trigger here, since its volume is already affected by the VCA itself. No need to double this up. Since the effect is, again, pretty subtle, let's do another before-after comparison.
At this point, our circuit is essentially a hybrid between the 909's kick and toms. This would have been enough exploration for me to go and fix my machine, but I wasn't done yet. I started thinking about ways to expand on the 909 sounds, and one technique that's absent from all of Roland's vintage drum machines is frequency modulation.
Frequency modulation, or FM for short, can create very rich metallic textures. It works like this. You take one VCO, which we'll call the carrier, and you modulate its frequency using the output of another VCO, which we'll call the modulator. This creates complex patterns in the output waveform of the carrier, which, depending on the relation between the two oscillators' frequencies, can sound really harsh and aggressive. To implement this in our circuit, we'll simply clone our existing VCO to create a modulator, with two slight differences. First, we'll use a significantly bigger capacitor in our integrator. This shifts the oscillator's frequency range downwards. This is desirable because it generally sounds more interesting if the modulator's frequency is lower than that of the carrier, at least in my opinion. And second, we'll push the Schmidt trigger inverter's thresholds further apart so we get a stronger output to work with. To mix the modulator's output with the tune CV and the pitch envelope, we'll simply use a 100K resistor. The resistor value directly determines the FM intensity here. The bigger the resistor, the less noticeable the effect. Also, I'll add a simple switch that lets us choose between applying the modulator's output or ground here, so we're able to use the circuit in regular 909 or FM mode. Right now, I've got the FM switch turned off, so our circuit sounds just like it did before. And here's what happens if I turn it on. While we do get some interesting sounds with the carrier tuned to a high bass pitch, it falls apart when I drop it down. What's up with that? Well, unfortunately, the carrier will crash into either supply rail when the input CV goes negative, which happens when the tune CV is not high enough to lift the modulator signal above the 0 volts line, making the output sound thin and weak. To fix this, we'll simply add a diode at the carrier's CV input. This will prevent it from going negative, even if the mixer's output does. And yeah, we get a much more solid output now with the carrier tuned low. Great. Here are some more examples of what you can do with the circuit in FM mode.
But while the circuit is already pretty versatile, there's still some untapped potential here. So far, we're only using our VCO's triangle outputs. They also generate square waves though.
And square waves, as I've learned by studying the TR-606 and TR-808 schematics, are great for synthesizing analog hi-hats and cymbals, at least if you use a bunch of them. We only have 2 though, and simply mixing them together would not give us a signal that's complex enough. So we'll need to fake having more oscillators than we actually do. For this, we'll use something called an exclusive OR gate, or XOR gate for short. An XOR gate is a logic gate that accepts 2 inputs and produces 1 output. If either input is high while the other is low, the XOR's output will be high. But if both inputs are the same value, its output will be low. With 2 dissonant square waves as our inputs, this creates a pulse wave with semi-chaotic pulse width that sounds harsh and metallic. Coincidentally, this signal is identical to what you would get from a ring modulator, which is why XOR gates are often used as a cheap substitute for true ring modulation. The Korg MS-20 is one famous example. To implement an XOR gate, we only need 4 diodes, 2 resistors, and a PNP transistor. It works like this. If both inputs are low, both the transistor's base and emitter are low, so no current flows through it and the output is pulled low by the resistor. If the top input is high and the left input is low, the transistor's emitter is pushed high and the base is pulled low, causing current to flow and the output to be pushed high. Same deal if the input states are flipped. Emitter is high, base is low, current flows and the output goes high. But if both inputs are high, both emitter and base will be high, cutting off the current flow and dropping the output voltage back down. As expected, we get a decently chaotic output from our XOR circuit. By adjusting the frequency relationship between the 2 oscillators, we can find some interesting sweet spots. For comparison, here's what regular mixing would sound like.
The XOR gate does add some strange metallic overtones, which sound great, but for proper cymbal sounds, the signal has way too much low end.
So we'll remove it with a simple Salon key high-pass filter. You can check my DIY hi-hat video for an in-depth explanation, but here's the basic gist. A Salon key high-pass is just a regular 2-stage high-pass with an added amplification stage, whose output is then fed back into the first filter stage. This makes the circuit's roll-off more steep, and it adds a bit of resonance. In our case here, we get a 12 decibel per octave roll-off, starting at 7.5 kHz and a pronounced bump at that same frequency, which should give the output a little extra bite compared to a completely flat filter. Because a transistor-based Salon key filter introduces a significant DC offset, we remove it with a simple coupling capacitor. And yeah, that does sound a lot thinner and more cymbal-like than the unfiltered signal.
Okay, so now we'll need to turn this static cymbal noise into a percussive hit. Thankfully, we can repurpose our existing VCA and Decay Envelope for this.
All we need to do is set up a simple SPDT switch before the VCA's input. Then we apply our sine wave output to one side of the switch, and the pulse wave output to the other. Because the pulse wave is much louder than the sine wave, we also need an additional 18K resistor to compensate. In combination with the VCA's voltage divider, this scales the pulse down to the proper input range for our VCA. Here's how this sounds with the VCA's input set to pulse wave and FM turned off. By tuning the 2 oscillators to different intervals, we can get a decent variety of cymbal and hi-hat sounds. Cool, but what if I also turn on the FM mode? The difference is subtle, but I'd say the additional modulation gives it a slightly more abstract metallic vibe.
With 4 different modes, single oscillator sine, FM sine, dual oscillator pulse, and FM pulse, our circuit now gives us plenty of manual sound design options. It's a little light on voltage control though, so let's do something about that.
First, I'd like to add a CV input for the decay envelope. Luckily, we can reuse another idea from my hi-hat video here. If we put a PNP transistor between the envelope's resistance and ground, the capacitor can only discharge to the voltage at the PNP's base, keeping the VCA open at that level. Since we still want the volume to decay further from here, if only slowly, we bridge the transistor with a big 470K resistor. This allows the cap to gradually discharge past the set CV level. This seems to work just fine. I can adjust the output's tail by applying different CV levels. Though to my ears, this seems most useful in the pulse wave mode for simulating opening and closing hi-hats.
Besides a decay CV input, it would also be great to have a tune CV input that controls both oscillators' frequencies at once, so we can play some simple melodies and bass lines. Good thing our circuit uses proper VCOs.
Because this allows us to simply mix our existing control voltages for VCO 1 and 2 with an external control voltage. There's only one small issue. Since we're using passive mixers for the tune CV inputs, the external voltage would interact with the other control voltages in unintended ways. Check the linked video for a deep dive into this issue. To work around it, we have to get a little creative. Instead of mixing the external voltage in, we can use it to modify the internal tune CV levels. It works like this. We add 2 PNP transistors between the tune CV potentiometers and ground. If we then apply a positive voltage to the transistor's bases, that voltage will be mirrored at the PNP's emitters. And if the voltage below the potentiometers is raised above ground, their output voltages will increase proportionally. There's one caveat to this solution. Since it's kind of a messy hack, we can't expect to get a volt per octave response. Still, we can make it somewhat tunable by adding a simple input attenuator. Seems to work just fine, except for one issue. If I try to set both oscillators to their lowest pitch, that lowest pitch is now much higher than what we got previously. What's up with that? Well, the issue is that our PNP transistors don't mirror their base voltages exactly. Instead, they add what we call a diode drop. So if we apply 0 volts to their bases, we get around 500 millivolts at both emitters, meaning that our voltage dividers can never go down to 0 volts. To fix this, we'll simply subtract the diode drop from the external CV using a diode and a big 1 megaohm resistor. It works like this. The resistor ensures that a small current flows through the diode at all times. And when a current flows through a diode, there will be a diode drop across it. So for 0 volts external CV, we'll get around minus 500 millivolts at the PNP's bases, which should then give us about 0 volts at their emitters. And yeah, sounds like our tuning range is back to normal. Great. Now that our circuit is complete, here are some example patches to show off what you can do with it. So while my 909 is unfortunately still broken, we did manage to create a pretty versatile and unconventional drum circuit, which actually fits in nicely with my previous drum circuits, since it can fill in the gaps and act as a tom, cymbal, or metallic percussion generator. And seeing how well they all fit together, Synth and I decided to work towards a big season finale, the DIY drums system. It will feature 8 modules in total: kick drum, snare drum, hi-hat, FM drum, compressor, and BBD. Plus 2 unreleased modules, a 4-channel drum mixer and a drum sequencer. More on those soon.
If you'd like to support the channel in the meantime, consider joining my Patreon.
You can get access to a bunch of bonus content like sample packs, circuit design essays, scrapped video scripts, and regular status updates. Or check out the other Eurorack DIY kits we've already released. You can get most of the designs on this channel as complete bundles containing a set of components, a PCB and panel, and an extensive write-up in the Synth's webshop.
The FM drum kit for following along with this video is now available too.
You can find links for all of these things in the description. Anyway, thanks for watching, and until next time. See ya!